So let's have a quick review before we move on anymore with, or before we look at this example, which is using a wheel wrench to loosen a bolt. So what we've talked about so far is last week we looked at problems where you might have a rigid body, but all the forces would converge onto one point. And so if you had some kind of object, and the lines of action rather of those forces would always converge onto one point within the body. In that case, to check for static equilibrium, all you had to do was add up the x components of the forces and the y components of the forces and make sure they were both equal to 0. What we're moving on to now is problems in which that's not the case, so not all the forces are up to 0. The simple case we've been looking at, or we looked at in the last example, was two kids on seesaw. Move them up a little bit. So in this case, primary forces is the gravity on the two kids, and you've also got a reaction at the center. And this time those forces don't converge onto a single point, and so in a situation like that, you have to add an extra condition for static equilibrium. And the extra condition you need is that the moments of the forces also add up to 0. So what was the moment of the force? It was simply the force times the distance to the support. And we'll look at that in a bit more detail later. There's a few more conditions to that, but force times distance is the moment. And if you're thinking about moments adding up to 0, then you need to be careful about whether a moment is positive or negative. And so we think about which direction does the force want to rotate the object about the support. So the person on this side, their force is tending to rotate that seesaw anti-clockwise, and right hand rule, thumb would be pointing up, that's a positive moment. The person on this side, their weight is trying to rotate that seesaw in a negative direction, and so that, in a clockwise direction, so that would be a negative moment. We talked about moments, and then we also talked about in this situation where the forces don't converge, it's even more important that the objects within that system are what are called rigid bodies, and so they don't deform so much that they change the problem. And we showed that with a very flexible seesaw. It would change this lever arm. If this bends all the way down here, the lever arm is going to change. It will change the problem. So rigid body doesn't mean it's completely rigid. It can still deform a little bit, as this plank would if they were using it as a seesaw, but it needs to be the case that it doesn't deform so much that it changes the problem. For this next problem, this problem talking about the wheel wrench, there's one more thing we need to introduce, and that's the idea of a torque. So a torque is exactly the same as a moment. We just use them in slightly different situations. So torque, T, again, is just a force times a distance. But often we'll use torque in situations where you've got small items that are rotating. And so, for example, if you were on site, you might have to tighten the bolts in a connection, and the design engineer, they'll tell you what torque to tighten those to. And so they might say, for example, you need to tighten this one to 300 Newton meters or something like that. What does that mean in reality? Well, if you had the spanner and you were tightening up this nut, so we're looking down on this now, and suppose the spanner was long enough, it would apply the force at about 200 millimeters. So this lever arm is 200 millimeters, so 0.2 meters. Probably a little bit unrealistic now I think about it. Suppose they told you to tighten that to 30 Newton meters, then you would have to apply a force of, let me just think about it, that's 0.2 of a meter, it's a fifth of a meter, and so this would have to be 5 times 30 is 150, so you'd have to apply 150 newtons here. I'm just thinking that through. Torque or moment is just force times distance. So we would have 150. Let's just do it. So make sure we see what we're doing. So let me just open up the little calc pad. So torque is just equal to force times distance. So to get a torque of 30 Newton meters, let's just check I've got it right. So it would be 150 newtons times 0.2 meters, because we've got our torque in Newton meters, which is 30 Newton meters. Okay, so to get the torque that the design engineer had told us to do, we'd have to apply a force of 150 newtons to this spanner, because we've got a 0.2 meter long lever arm. Another time you'll find torque talked about more is when you're talking about motors, and so you'll see the motor has a certain torque at a certain speed. Now, the stalling torque of this motor, so in here, once you start to get situations like this, it's harder to see where the forces and lever arms are, and that's one of the ways you can say, well, this is more appropriate to talk about torque. But if you said this had a certain torque, so say again, this had a torque of 30 Newton meters, that would mean in order to, if it's a stalling torque, that's about the torque it can apply from the stop position. Then if you had a lever clamped onto this that was 1 meter long, that would mean that you'd have to apply a force of 30 newtons to stop that motor rotating. So 30 Newton meters. So to stop that motor rotating, you'd have to apply a force of 30 newtons at a distance of 1 meter. And that's where the torque comes. Now it gets a little bit more complicated because they also have a torque when they're spinning, and that would be the force you need to apply to keep it spinning at a constant speed. And that's the torque of the motor at a given speed. Okay, so that's moment and torque. At this stage, just need to think about it in terms of they're the same thing. They're just used, the two terms are used differently in different situations. Usually you'll talk about torque when you've got like a shaft or a small nut or something like that. And so let me just, I should have just moved those to the side actually, so I can put them in the notes for you. So let me just do that. I hope. Cool. Okay, so what's it asked us to do? Well, let's just do one more thing as well. One thing here is, so when we were looking at the seesaw, it's quite easy to see where the balancing moment is. You've got a moment on this side and it's balanced by the person on the other side. When we start talking about spanners and wrenches and motors and that sort of thing, it can be harder to see where is the balancing moment coming from. So in this situation, someone's pushing down on that wheel wrench with a force F at 200 millimeters. So there you've got your moment. So it's going to be force times 0.2 meters. But what's stopping that rotating? Where's the balancing force and lever arm? Well, what it would be is, if you imagine looking at this little nut down here, what I'm going to do is a section view. So I'm imagining cutting off the head of that torque wrench so I can look inside. And so this is your, not torque wrench, it's a wheel wrench. So this is the wheel wrench cut through the wheel wrench so I can see the nut inside it. And so if this person's pushing down, that socket is going to rotate around until it contacts the nut. And so then it's going to contact the nut. Let's mark on where it's hitting the nut. So it's hitting the nut here, here, here. Okay, just marking on where the wrench is contacting the nut. And so we had this guy applying a moment and it's a positive moment on the torque wrench, on the wheel wrench. So positive moment anti-clockwise. The reaction to that is the reaction where the socket of the torque wrench hits the nut. The nut is going to be pushing back with a force at each of those points. So the nut will push back, it'll bear onto the nut, the nut will push back onto the torque wrench, like so. Each of those forces has got a tiny lever arm that's just the diameter of the nut, really. And so all of those forces plus the lever arms add up to a torque in the opposite direction. So the torque is tending to turn that way, which is clockwise, so it's negative. And so this moment will be cancelled out by the moment as a result of all these small forces where the nut is contacting the torque wrench. Okay, so back to this problem. These ones I'll just move out the way as well. So let's go through the problem. It's quite a lot of intro for quite a simple problem, to be honest. So force of 100 newtons is applied. What will be the moment? What moment will be applied to the nut by the tire iron or tire wrench? So we've got force. So this force is 100 newtons is what it's saying. And it's asked for moment. You'd have asked for torque. Would have been the same answer. If it said what torque will be applied to the nut by the tire iron, and we've got the same answer. So moment equals force times lever arm, which is equal to 100 newtons times. So we're just thinking, we're wanting, usually you'll give your answer in Newton meters. You don't tend to give answers in Newton millimeters, but you might for very small things. And so I'm going to change this 200 millimeters to meters. So that's 0.2 meters, which is equal to, move that 2 places, 1, 2. So we just stick on a 0 if we don't have a place. You know, all this stuff from school. So we're going to end up with 20 Newton meters. Answer the question. Moment applied to nut equals 20 Newton meters. So for part B, saying, so usually if you're putting nuts back on a car wheel, you just give them a bit of grease first, and that stops them seizing onto the bolts that are in there as they corrode. In this case, they forgot to do that, so they estimate that they'll need a torque of 400 Newton meters to loosen the nut. What force will they need to apply at a distance of 200 millimeters to loosen the nut? So this time they've talked about a torque. It doesn't matter, it's the same thing as a moment, it's just they're used in different situations. So again, torque is equal to force times distance. This time we know the torque. So we know the torque is equal to 400 Newton meters. And we also know the distance is equal to 200 millimeters. We just need to be consistent in our units, so 0.2 meters. I'm going to substitute those into the equation. So therefore 400 is equal to, force is what we're trying to figure out, times 0.2. Divide both sides by 0.2 and swap them around. So it's going to be 400 divided by 0.2, which is going to be 400 is the same as times 5, so it should be 2000 newtons, I think. 400 divided by 0.2, 2000 newtons. It's quite a lot. 2000 newtons. So force, just again writing out my answer. Force required to loosen nut equals 2000 newtons. Now, always when you're doing maths or engineering problems, you should be thinking about what does that mean? So 2000 newtons, well, we're less used to using newtons than kilograms, so we can think about the equivalent weight or mass. And so 2000 newtons, the simple way to change newtons to kilograms, we divide by 10. So that's about a force that's equivalent to a 200 kilogram weight on Earth. So 200 kilograms. Why do we think about that? Because they're saying that the car owner weighs only 65 kilograms, so they're not very heavy. And so, do you think it's possible for them to loosen the nut with this wrench? I think it's going to be unlikely. So you can imagine what you sometimes do if the nut on the wheel's seized on, you'll actually stand up on this. It's probably not very safe, but you stand up on that and bounce up and down a little bit, and that sometimes loosens it off. Now you have to be careful with that. In case you fall off, you'll hit your shin. But a rule of thumb that engineers often use is if you're jumping up and down on something or essentially bouncing something, you'll get a force that's about double your weight. And so they might get a force that's equivalent to 130 kilograms, so that would be 1,300 newtons. So still not going to be able to manage that. Even if they stood on this wrench, they still wouldn't manage that. They could pull, let me have a think about this, they could take this wrench and put it on the other side to loosen a bolt anti-clockwise. So you'd be going this way. And so they could put the wrench on that side and go that way, and you can actually lift a higher load than your own weight. But pushing your luck for someone who weighs 65 kilograms to put on that sort of force. So we've kind of exhausted the options. What option is left? Well, what you can do is you remember that force, torque, let's talk about torque in this case, is force times distance. So if you don't want to apply such a big force, what you can do is you can increase the lever arm, the distance. So what they could do in this case is they could get a nice long pipe, if they've got one lying around in the garage, and slip that pipe over the top of the wrench. Let me try, I'll sketch it down here. So you've got your wheel like so. You've got your wheel wrench on here, which is not very long. So you just get a nice big long pipe, put that over the top, and then apply a force on that. So if this person weighs 65 kilos, so they could get a long pipe, and the longer you make it, the better. Every time you double that length, you're going to half the force you need to apply. And that means if you get a long enough pipe, you'll be able to loosen off that bolt. So let's just have a think about what that means in this case. For someone who weighs 65 kilograms, might be reasonable. I'll put this in green. It's not part of the, it's not part of the question, or it's not part of the answer. They haven't asked us to do any calculations. They've just asked us what we do, but I just want to make sure it's sensible. And suppose, so we're trying to achieve a torque of 400 Newton meters, I think, wasn't it? So we're trying to get a torque of 400 Newton meters, or a moment of 400 Newton meters. A reasonable force for someone who weighs 65 kilograms to apply might be, say, 30 kilogram equivalent force. So that might be 300 newtons. So that might be reasonable. So let's see how long the pipe would need to be. So torque is equal to force times distance. In this case, we're going to be putting in we need a torque of 400 newton meters. We can apply a force of 300 newtons. We want to figure out what lever arm we're going to need. So the lever arm is divide both sides by 300, 400 over 300, which is 4/3, which is about 1.33 meters. So that's reasonable. So you just need a strong pipe. Obviously, you're going to need a steel pipe or something like that, 1.33 meters long, and they'll be able to loosen that nut. So how would we answer this question? I'll just make that green actually. So they should increase the lever arm. For example, e.g. by using a steel pipe over the, sorry about my writing, the wheel wrench. I'd like to say it's just because I'm writing fast that it's untidy, but it's not. My writing's just untidy. That would be a decent answer for that. Should underline it, I suppose. Looks a bit silly. Of course, there's other ways to loosen that nut. The more sensible way would be to get yourself some WD-40 or RP7 and spray the nut, wait for 10 minutes, and then try and unloosen it. So those WD-40 and RP7, they will get into that nut. It's like an oil, a very thin oil that'll get into that nut and unseize it. But if you don't have any of that, you could use a pipe. Just be careful. Right, next question.